I'm Michael Drummond, Principal Scientist at Chemical Computing Group. Today, I'm going to show you how to perform solvent analysis on a protein-ligand complex. I'll walk you through how to set up the simulation and then go through a couple of typical analyses. With these workflows, you'll get an understanding of the interaction of your system with water and how to rationally improve these interactions for better ligand binding in just a few minutes. Let's get started. As you can see, I've already loaded 4RFZ, a crystal structure of the kinase BTK in complex with an inhibitor, shown here. There's nothing particularly special about this crystal structure, but it is high resolution, so there are a large number of crystallographic waters we can compare our predictions to, and the inhibitor is quite large, which should give us many predicted waters to analyze as well. In the interest of time, I've already prepared this structure, but I did skip the minimization part of quick prep to leave the crystallographic waters at their experimental positions. I've also already annotated the kinase motifs, so we see the hinge in gold, the G loop in green, and the DFG in cyan. Let's launch the Solvent Analysis tool from the top of Mo via Compute, Simulations, Solvent Analysis. At the top, you can see the two modes, binding and solute. Most of the time, you'll want to stick with binding, which is suitable for a complex, whereas solute is used if you only have an apoprotein. The next set of settings define our input, and the defaults are good for most use cases. You'll notice that we are only including receptor atoms, not receptor plus solvent, for our receptor, and so our crystallographic waters are not included in the simulation. Although we'll be able to compare our predicted results with these crystallographic waters after the simulation. Next, we can provide a file name. For example, I'll just put the PDB code 4RFZ. The Solvent Analysis tool always predicts the position of water molecules, but optionally you can predict regions where salt or hydrophobe are enriched in concentration, although we won't be doing that today. Generally, the defaults on this panel are suitable for most scenarios, with one exception. If you're analyzing a particularly large system, such as a protein-protein interface, or if your computer does not have much free memory, then you'll want to uncheck the simultaneous run option. With this box checked, the simulation will automatically calculate the water packing of three systems at the same time: the isolated ligand, the apopocket, and the holo complex. If you uncheck the simultaneous run option, these three simulations are performed one after another, which requires less memory, but does take longer. If I were to click Run, then the Solvent Analysis simulation would proceed. On my 2-year-old laptop and this exact system with these settings, this simulation takes 7 minutes. Instead of waiting, I'll close the Solvent Analysis panel and even close my currently loaded system to show you how you can revisit your results at a later date. I'll click the Open button, and as you can see, there are multiple log and .rism files in my current working directory. Double-clicking on any of the .rism files will open up the results. I'll also click Yes to this question, since I do not have my system in the main Mo window anymore. The Solvent Analysis Sites panel appears, and our predicted waters are shown as red, green, and gray spheres in the main Mo window. If you run Solvent Analysis yourself and you do not see these spheres, contact us at support@chemcomp.com, and we'll send you the script you need to see these spheres. The Solvent Analysis Sites panel controls the spheres, the predicted water sites, in the main Mo window. At the top, you can select which system you want to visualize. Currently, we're looking at the waters for the protein-ligand complex. The main portion of this panel contains information about each predicted water, such as its occupancy and its predicted free energy. We also see information comparing the predicted waters to the crystallographic waters. I'll sort by the distance column and then select the predicted waters less than 2 angstroms from an experimental water. By selecting them, we now only see these waters in the main Mo window. And as you can see, there are a large number of accurately predicted water sites, giving us confidence in our predictions. For clarity, I'll now hide the experimentally placed waters, and I'll deselect everything from my list. The spheres in the main Mo window are also colored by free energy, where a green site is stable with a negative delta G, which means it costs energy to displace. By contrast, a red water site is energetically unfavorable or unhappy. The main use case of the solvent analysis application is to use this information about the solvent environment to improve ligand binding potency. And so now I'll show you two simple workflows to help you do this analysis. First, I'll toggle over to receptor mode, which shows how water packs around the apo pocket of the receptor. For this part, I like to only show waters within 2 angstroms of our ligand, as these waters are directly displaced by the ligand as it fits into the pocket. What we're looking for are green, stable waters being displaced by the ligand. It costs energy for our ligand to displace these apo waters, and to mitigate this cost, it's best if the water is replaced by a polar atom on our ligand, such as nitrogen or oxygen, to best mimic the behavior of water. For example, we can see a stable water near the hinge being replaced by a carbonyl oxygen, which is okay. There's also another carbonyl oxygen being replaced by replacing a stable water on the bicycle, which is also fine. However, the same bicycle, you see here, there's a minus 4.2 stable water, which is being displaced by a fluorine on our ligand. Thus, solvent analysis in receptor mode suggests that replacing this fluorine with a more polar functional group might be an easy way to improve our ligand affinity. For the second workflow, let's return to viewing the predicted waters in the complex, and I'll also return the viewing distance back to the default of 5 angstroms. Before starting this analysis, I want to take a minute to talk about this occupancy column. This occupancy is quite analogous to the same concept in X-ray crystallography, so that high occupancy waters are more confident predictions than those with low occupancy. I often sort the complex waters by this occupancy and then select only those waters with greater than about 0.3 or 0.4, so right about there. And so this hides the display of low confidence waters. Now, for the analysis, the simplest way to improve ligand affinity from a solvent perspective is to grow your ligand and thereby displace an energetically unfavorable red water. And we see there are a lot of red waters in this system. However, if I turn on a van der Waals interaction surface of the pocket, you can see that most of these red waters are actually at the interface between our bound ligand and the pocket and bulk solvent. So displacing these red waters simply indicates that we can grow our ligand into the solvent without an energetic penalty, which we already knew. Instead, we'll want to focus our analysis on those waters at the bottom here, those trapped between our ligand and the receptor pocket. For this next part, for this analysis, I'll hide the ribbons, and then we'll look. For example, I see right here in the middle a very unhappy water at almost positive 6 kcal per mole. It's a bit far from our ligand, but if we could grow the ligand to displace this water while avoiding this nearby stable water, I would expect quite a significant potency gain. There's also another water here, only positive 1.4 kcal per mole, but it is another opportunity. Again, it's a bit distant from the ligand, and I'm not sure that the growth vectors are readily accessible. But if we could do that, if we could grow our ligand to displace this water molecule, we should get a slight gain in potency. And this one at least doesn't have the complication of a nearby stable water. Finally, you can also look at this analysis in another way. For example, I see we do have a stable water molecule right here, about minus 3 kcal per mole. Now, I wouldn't want to grow my ligand to displace this water, but perhaps I could add a polar group somewhere on the dimethylamino, which could turn this water at this predicted site into a stable bridging water, which provides another complementary means to improve my ligand affinity. There's much more we can do with solvent analysis, but at least I hope today I've shown you some quick, easy analyses that can be done in about 10 minutes. As always, if you have any questions, please reach out to me at support@chemcomp.com.